Hello, ladies and gentlemen. Welcome on our first lecture after a break. I finally am able to speak again, and hopefully I will be able to do it more longer. And today's lecture is a continuation of our previous lectures that were available to you through video with my edits, and we'll continue linear models. The topic of lecture 4, which will be probabilistic computation, will happen, but not today. I'm not sure when, but it will happen certainly in this next week or a bit later than that. Fortunately, it's not that important for us at this moment. However, I will keep the formula that was previously, that is the lecture that is joining both the slides and discussion of Jupyter notebooks, which are available to you since I think Sunday on the GitHub. So if someone was interested, could look at them. And we'll focus on linear models because linear models are the backbone of all statistical and mostly machine learning also approaches in practice of data analytics, because generally we always want to have to model some kind of relationships. We often don't know what those relationships are, and linear relationship is always the some kind of an approximation. If you remember from physics that sine function can be approximated with an angle of the sine of an angle can be approximated with an angle. If we consider it in radians, it was linearization. If you remember control theory, the backbone of the entire control theory is linearization, that all processes can be at least locally modeled by a linear process. So that's why linear models are important, and of course they can work also in the different approaches. In control, we had a complicated model that we were able to construct using laws of physics or laws of mass conservation or some other underlying knowledge, and then we could linearize that linear model. In case of statistics, we just assume that the linear model is at least locally good, and then we want to use it to approximate the relationship. And that's the idea of linear models in statistics, that we estimate the parameters of linear model, and hopefully it will work. This approach also works in control. This is an approach of linearization by identification, that you just use one of the identification methods to fit a linear model to a nonlinear process, but around certain equilibrium or set point. In such situation, then that model works and it can be useful. So, without further ado, let's go into linear models, because generally linear models are called maybe I'll just one more thing. Today's lecture is strongly based on the book of Richard McElrath's Statistical Rethinking, 2nd edition. We are using data from Richard McElrath's package, and we are considering the same examples. And also this picture is also from this book, because this is generally the main idea that kinda explains what we are having with linear models. Because even in the ancient ages, in the age of Ptolemaios, there was a model of solar system created with the assumption initially that all the planets, stars are traversing the sky on circles, on circular orbits. And of course they don't. We know now they're on the ellipsoidal orbits. However, in those times, in order to compute that, they've seen that, okay, circular orbit does not work, so maybe epicyclical orbit works. What is an epicycle? Epicycle is that instead of movement on a circle, we move an additional circle on a circle. That is, when we have this big circle, the smaller circle moves around it with the point in the middle, and after that, and around this middle of the smaller circle, our object actually moves. So the middle of its revolution revolves on this one circle, and it's by itself moved on its own circle, something like an orbit, in a sense like an orbit of this second virtual circle. These are the epicycles. The idea was that introduction of epicycles actually improved the representation. So from the data analytical point of view, this model was very accurate. It allowed us to predict the movement of the planet regarding Earth, and it is very, it's also very, it's kind of nice. But we now know that planets do not revolve on the epicycles; they revolve on ellipsoidal orbits. So why this one worked? This one worked because actually it's a very naive Fourier series representation of a periodic orbit. Additional epicycles, because you can always add an additional epicycle, additional circle, which moves around this circle, which moves around this circle, and adding additional and additional with increased complication of computation, it's still it improves the computation quality. Why? Because it's an, in a sense, representation of the movement as a Fourier series without using Fourier analysis. So this approach led to good results, but of course it does not represent the causal relationship of what we observe and what is factually going on. So we have a physical situation, we have a system that is revolving, the system of planets and stars in the universe, and the movement has its own underlying phenomena, which is not captured by our model. However, its numerical values, its predictions using our model are very good, or at least very accurate. And this is very often a case with statistical models, and with even more extent with machine learning models, because models are very good at predictions, but they do not represent the phenomena. The best example are, of course, neural networks, because all the processes that are realized using deep learning are not really representing the process. When we are using different machine learning methods like decision trees, we know that the phenomena is not a decision tree. We know what's going on, but the decision tree is a good predictor or a classifier in that case. So that we can use it because it gives us good quantitative information. It does not give us qualitative information. So we know, we get the numbers right, we don't have a model that represents what's going on. So is that bad? No. For certain applications, it is very good. However, we need to be careful when making decisions based on that, because if we make decision of changing certain parameters, especially after or variates outside of the known model, outside of our previous expertise, our model might lose sense, because in such situation it is not the it was never describing the causal relationship, and because we got out of its comfort zone, it got also it started giving wrong predictions because it didn't have any base to predict right. This is a problem of generalization. And that's the general idea of creating a models that we know that are not really true, but are still useful. Because again, linear model, not really true, especially not in large scope. However, it can lead us to good predictions, and sometimes enough. Also, it can also be sometimes describe causal relationships, but this is a more advanced topic that probably we won't be covering in this course. So, generally, what we will be considering today is regression. at least what is called in statistics as regression, because our regression models are used to explain relationships between independent and dependent variables. So independent variables can be those things that we measure, and dependent variables are quantities that we are interested. For example, classical, we know the parameters of a wine, we want to predict its price. This is the classical regression model. However, what we really want is that we want to create models that are used to determine a numerical value. Those models with careful analysis and good understanding of the process can also be used to explain relationships in more fundamental way, but we need to know what's going on. We need to analyze it in the context of cause and effect and laws of physics and general logical relationships that must be covered in order to everything to work. So that's the main idea. Okay. And what we are really doing here will be general linear regression, which is based on the Gaussian distribution. Because generally we will be interested in models that are behaving in accordance with normal distribution. This is not the only case. We can use generalized normal distribution, for example, using student t-distribution, which you've seen in the example with the Newcomb experiment. However, generally, we are focusing on the normal distribution, so we assume that y is normally distributed with mean mi and standard deviation sigma when it is a random variable from the distribution. And in our Bayesian context that we are covering during this course is that we are uncertain about an actual value of y, but our uncertainty can be described by a normal distribution. So we know that our measurement process relates the underlying relationship in the form of a normal distribution. That is normal distribution. There is some kind of mean value, and there is some kind of the uncertainty covering it that is covered by the standard deviation. So we have two parameters that give us the coverage of variable y, and generally we always want to find a description of our uncertainty about the problem, because knowing that we can make inferences or predictions with margins of safety that we can find, because in the situation of uncertainty we almost never are able to exactly predict the value of interest. We can, however, predict it with some kind of bounds. In simple cases, those bounds and value can be determined analytically. In more complicated situations, we can cover it by estimating the distribution of this measurement process, for example, using Monte Carlo simulation. And we want to find such description in one or another way in order to create this model. And statistical models are generally like robots or computer programs. Then they process data, but if data is bad, the results will be bad. If we teach them bad, they will learn badly. And in case of Bayesian modeling, we kind of get the uncertainty about our data, about the process, encoded in our model. And we encode it with probability distributions, and that's why normal distribution is here popular, because of its many desirable mathematical properties and also certain relationships that make sense. Because generally Gaussian distributions are everywhere, and they are but they are not everywhere as much as we would think. Not every distribution we see is Gaussian, because they are often not. But very many processes behave Gaussian-like. First of all, we know from the central limit theorem that you should kind of remember from the probability course on the first year of your studies, is that sum of identically distributed independent random variables is normally distributed. This abbreviation IED is independent, identically distributed random variables. So if we have sum of those variables, it is normally distributed, which is very important, for example, in Monte Carlo computation, where we compute expectations, which gives us the central limit theorem as a power for Monte Carlo error estimation. But that's will be covered on a lecture that should happen before, but that's a tangent. So let's start with a very simple thought experiment. Let's imagine us that we have a football field or any other sport field, and you get 1,000 people and tell those people, okay, you stand in the middle and then move randomly into any direction as long as you want. Let's say no more than 1 meter. So you will move, okay, you move along the line and you just move either left or right randomly, and you move randomly with randomness. So generally you take a step with, mathematically speaking, of uniformly distributed between -1 + 1 meter. So you just move this way. So how the positions of those people will behave after making those steps. So how they will walk around the field. And we can actually see that numerically, because by performing a very simple calculation, we can see that people will be covering more and more. Starting with the middle, they just move they move no more than 1 meter in each side, but because there's a lot of them, we can see how this behavior changes. And this distribution of those steps, because look at this, each of those steps, after some number of steps, we get the sum of identically distributed steps, because the length covered, or the position in this case, will be a sum of steps with positive or negative direction. So from the central limit theorem, they should be normally distributed, those positions of people. And this can be observed even after 4 steps, that we get some kind of bell-shaped curve. After 8 steps, even more visible. After 16 steps, we get a very nice curve that fits it very well. So generally, by observing such, for example, movements, we get the normal behavior. The sum of identically distributed steps leads us to this situation. Okay. So generally, the normal distribution is good for multiple things. So we have the processes that are a form of increments, which are very often happening. So we have an increments, those sums will be normally distributed. This is also true for a small percentage changes. So if we multiply by numbers close to 1, this behavior also is normal-like, but this comes from the linearization actually. And if you multiply by large numbers, we have a normality on logarithmic scale, because you get the log normal distribution, which is exactly that, normal distribution on log scale. So if you have repeated operations on the on a number, so we have series of steps that are covering the situation, either by multiplication or addition or combination, the result will be normal-like, at least on some scale. So it is very important. So it seems that this normal description is rather important in practice, especially that, for example, this comes again with errors and stuff like that. So what we I started recording by an accident. Okay, sorry. I've removed my camera by an accident. Hopefully I will be able to cut that. So okay, that was a interlude, a technical issue again. So of course, sorry. Okay. Fortunately, I'm recording this, so maybe I'll be able to cut it later and edit it, so it won't be that irritating for people watching that later. For live viewers, sorry. Generally, what we have here is that when we construct our model, we must focus on what are we doing here. First of all, we need to recognize the set of measurements that determine the outcome. So we need to determine what are our variables of interest, what is the outcome of interest, what we observed, what data we've collected. Then we define the likelihood, so the plausibility of individual observations. So how the uncertainty is present in this relationship. So in linear models, it is usually Gaussian relationship, because it gives us the ease of computation mostly, and also if we do not have any motivation of extreme values happening here, normal keeps us rather tight in the neighborhood of 2 sigma from the measurement. So this gives us a little bit of leeway. So then we want to recognize the measurements that we want to use to predict our outcome. So we need to split our variables into dependent and independent. Then we need to construct our likelihood, our predictive behavior, based on our predictor variables. So we define the predictors, and then we define what parametric relationship is between those predictors and the model's parameters. And when we have those model parameters selected, so for example weights of the linear combination, we choose the priors for the model parameters, and then we fit the model. So we have priors, and then we go to the and then we can move to the our relationship. And how to practically do it? We can use these. We can create it using standard Bayesian formalism. And this formalism says us generally that each of the outcome measurements is normally distributed with respect to certain mean and certain standard deviation. Look at it, however, that those means corresponding to each outcome are also indexed. Why? Because they are related to the predictors. Each of those means is a function of predictors. So in our case, we have an intercept, which is a standard name in statistics for such behavior. So we have a constant parameter that is the described by our relationship. That generally gives us the average value when all the predictions are equal to 0, and beta parameters are the parameters corresponding to the predictors. Because you can more than one. You can have multiple. Then this can be a vector. B also can be a vector in a sense, or a matrix. Generally, what we have here is that outcome is normally distributed with, in this case, fixed sigma, with a mean that is a function of predictors. In case of linear models, it's a linear function of predictors. And in practical applications, we want to give some kind of priors for those parameters, and usually good priors are some kind of regularizing priors. If we don't have any base for relationships, because for example, if we know that there's a positive, we are sure that there's a positive relationship between predictor and the outcome, then we need to focus on how to express that in the prior, so the prior will leave us in the right place. However, if we don't have such information, then typical choices are normal distributions, which gives us generally that they limit our, let's call it, search space of parameters that we are looking for parameters, but it adds them to the it makes it smoothly by generally limiting the probability of going more than 2 sigma away from the value. In case of prior for sigma, then we usually, of course, sigma has to be positive, so we need to use some kind of asymmetric distribution. And typical choices are either Jeffreys prior, which is our ignorance. Exponential prior is very good because it's a bit heavier tailed than Gaussian, but it's still rather light tailed and gives us the information. Or in case of, and we can also use half normal distribution. That's to estimate to provide the prior for our sigma. So half normal is the lighter tailed distribution that is more focused around 0. In why we want something heavier, because we might want to be prepared to give a bigger standard deviation than initially expected. So we want to leave some probability available to sample there. So this is almost a classical linear regression. Why? Because classical linear regression is this part. These two lines. In case of, in classical linear regression, we have a normal distribution. However, what we have in the classical nomenclature is that all priors for those parameters are flat. And also sigma is not being estimated. So we just assume flat priors, so uniform distributions, no, without any bounds, any number is okay. And then the solution for this system is, of course, standard pseudo-inverse matrix of the design matrix, or so-called the matrix of predictors. But in Bayesian formalism, we assign priors, so this can be very useful because thanks to that we can avoid the problems with the that can be with the for example, hard to identify models. Okay, so as I mentioned earlier, linear models are justified by Taylor expansion because locally any function can be expressed in a linear using only linear terms, and the problems is, of course, like generally the problem is with locality. The problem that is not always visible in in analyses given by the humanists, economists, and people like that, because in their behavior they sometimes forget about this locality requirement, and they just focus, oh, there's a threat. But if we move on the same scale, those linear relationships are justified. If we have any background knowledge that justifies linear relationship is justified. However, if we do not have, then constructing linear relationship between one and the other variable is unfortunately not very responsible.